Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support. Hey listeners, it's Mike. While Nanovation is a niche podcast, it'd be great to share it with more people. And I think the easiest way to do that is to leave ratings and reviews at Apple Podcasts, or wherever you download the show. Now hopefully your ratings and reviews are 5 stars and say this is the best podcast you've ever listened to. Kind of like Happy Kitten 62. This person said, I discovered this podcast after I went to Dr. Filler's amazing talk at a conference and looked up his name. Now, I don't know what conference that was, but I'm glad you thought the talk was good, and honestly, I wish more people would say that. Doesn't everybody? And this person went on to say, this is a great podcast for anyone interested in nanoscience and technology. It addresses a wide variety of interesting topics to get everyone interested and provides comprehensive information on each topic, such that it is easy enough for a general audience to understand the content. Overall, a great podcast, and I would recommend it to everyone. Well, thank you, Happy Kitten 62, for such a glowing review, and I hope many of the listeners out there enjoy the show enough to write something similar. And now, on with the show.
The person that was performing the autopsy chose to take out his brain, chose to take out his eyes, sent his eyes to his ophthalmologist, kept his brain for himself, cut the brain into 240 blocks, which gives you about 1,000 slides of brain tissue, and apparently sent these slides to researchers around the world.
That's Elizabeth Nance, a professor of chemical engineering and radiology at the University of Washington. She's recounting the fascinating tale of what happened to Einstein's brain after his death. The story is relevant because the Nance laboratory studies the use of nanoparticles for the treatment of neurological diseases that originate in the brain. We discuss what makes nanoparticles such interesting drug delivery vehicles, how her lab interrogates these complex systems, and why laboratory success so often fails to translate into actual people. And be sure to listen to the end to hear Elizabeth's unique perspective on interdisciplinary training in the 21st century. When a conversation begins with a story of a stolen brain, you know it's going to be good. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. So today it's a real pleasure to have Elizabeth Nance. She is the Claire Booth Luce Assistant Professor of Chemical Engineering at the University of Washington, and she's been there since 2015. Welcome.
Thank you for having me.
It is my pleasure. I should say you're also an adjunct professor of radiology in the School of Medicine. That must be interesting to bridge those two groups of people.
Yeah, so it was a big part of my faculty search process was finding somewhere that was interested in supporting an adjunct appointment in the School of Medicine. I felt like it would be very valuable to have that on paper in a formalized way, that I was acknowledged by medical faculty as being somebody who had or could have medical and clinical impact. And then just getting the timing of when I was going out for my interviews aligned really nicely with a lot of School of Engineering's and particularly chemical engineering departments push to have more direct connections to School of Medicine faculty or School of Medicine appointments. So it worked out really nicely. It usually gets an eyebrow raise when I go somewhere and, there's somebody looks and says, oh, wait, you're appointed in the School of Medicine as an adjunct. I'm like, yeah, but I don't have an MD, and I kind of explain why that School of Medicine appointment is there. But it's always it's a good, learning opportunity for others to know that that's a feasible path as well.
I guess at some level, it's what you're saying is it's the stamp that if you submit a proposal to some part of NIH that you have some extra street cred.
Yeah, street cred was definitely a concern of mine coming out of my PhD and wanting to do really clinically focused or clinically driven research. So doing a lot of in vivo type work, I felt like was going to raise a lot of questions about me being a chemical engineering doing that. So my postdoc training was in part to kind of build the skill sets to fill that gap that people might view otherwise. And then the medical appointment on paper was something that I just learned during my postdoc, that if I had given a talk, for instance, in a clinical department, that opened a lot more doors because it said the clinical department was interested in having an engineer come talk about this. So they found it useful or relevant. And so having those kind of formalized things that you can literally just put on paper, and I can also hopefully always back up, seems to be helpful in just opening doors that allows for ease of access to collaborations, but also, access to student base that maybe would be good to have in the lab, like MD, PhD students or biology or neuroscience based students. But then also just more funding opportunities that maybe wouldn't normally be funding opportunities that a chemical engineering faculty might try to take, and that if a review committee sees, wait, this person's in chemical engineering, they might raise an eyebrow about. So
right, they're wondering where the oil is.
Right. Yes, I don't do any chemical production or petroleum or
Right.
or any of the more traditional kind of foundational fields that chemie was built on.
Yeah, it reminds me when I come back from travel abroad. Sometimes there's, what do you do? I'm an engineer. And I don't say chemical engineer, sometimes intentionally.
Yes.
You never know what the response is to, oh, you're a chemical engineer. It's not connected with bad things. And it turns out to be connected with a lot of good things, but people take it different ways.
Right. I know. I do a very similar thing. And I think it immediately elicits this view of, either very, very kind of quote unquote old school chemical engineering or somehow very negative, implications of what that can mean. And it's, I think it's something I actually try and teach students about, is that, we really have to start to dissociate ourselves from actually the name of a degree, because degrees are so interdisciplinary now and they can mean a lot more than what on paper they seem to mean. And so it's important not to, derive everything that you think you are, everything that you want to do based on just the name of the degree, because chemical and to most people means something to do with chemistry. And I would argue that physics and math underline most of chemical engineering more than chemistry does. And so that's usually kind of a surprise to undergraduate students, because you're like, oh, if I go into chemical engineering, I don't really like chemistry, so I don't want to do that. And I'm like, well, that's cool, because we don't actually do all that much chemistry in the majority of our core classes. It's there, but math and physics is, equally, if not more important in a lot of those concepts and fundamentals than chemistry is. So it's always an interesting, discussion that comes up out of it.
I completely agree. And I say the same thing to students, and I'll let them know that, jokingly, we don't care what we make, but we want to make it efficiently and make it in truckloads. And so most of that is a lot of physics.
Right.
It's a lot less the actual A goes to B. Who cares what A is and what B is?
Right.
But the rest of those things that make it efficiently and make it in large quantities come from a different discipline.
Right. Yeah. Yeah.
Well, very cool. So there's a lot I want to talk about related to interdisciplinarity and things like that, but let's hold off on that. Let's talk a bit about your specific lab's research first.
Yeah.
I guess we'll start with the article you sent me. And I will say to everyone who's listening, I ask all of the guests to propose a short news story, perspective article, something that's a page or two, that's easy to read, but talks about something interesting that hopefully is related to their research or something they want to talk about. And, with the proliferation of science communication these days and science journalism, there's an endless supply of these kinds of things. And I received from Elizabeth an article titled Einstein, A Stolen Brain, and a Mystery. And I will say it's the best article I've received for the podcast. Elizabeth, why don't you explain a little bit about what this article is talking about?
Yeah, so this article was fascinating to me for many reasons. First, anything to do with mysteries and sort of missing brain tissue is curious. I found that intriguing, and particularly from the perspective of coming from a training place like Johns Hopkins that has a long history of taking tissue and cells. I mean, we can think about like the HeLa cells, for instance, taking tissue and samples for analysis without actually fully being transparent about what their purposes of that was. So this kind of title caught my attention, both from just from that mystery perspective, but also Einstein's brain, like the IQ of Einstein was so much higher than the average person. I think it was like somewhere in the 160 to 190 range, and the average person is somewhere between 90 and 110. And how much IQ is relevant to actual, intelligence is beside the point, and maybe a different discussion. But I thought, in just kind of reading through the article, one of the things that they were really focusing on was how much information was there within this brain that was taken to do pathological analysis on, to try and understand why Einstein was so unique, why he had this capability to do and think in such a different way and in such a higher, level way than so many other people. And so the pathologist that the brain was sent to, or actually the person that was performing the autopsy, chose to take out his brain, chose to take out his eyes, sent his eyes to his ophthalmologist, kept his brain for himself, cut the brain into 240 blocks, which gives you about 1,000 slides of brain tissue, and apparently sent these slides to researchers around the world with the intention for a lot of different people to study these slides, and then for him to write a book on it, which, by the way, never actually ended up getting published. And so some of the things that the researchers were looking into were specifically what was different about Einstein's brain from the average person. And so they took other post-mortem brain samples from patients in a fairly wide age range, like at least male patients, but in a fairly wide age range, where, it covered Einstein's age, which I think he was 76 at the time that he died. And they started looking at the sort of total brain versus some of the more nuanced sort of microstructural differences within the brain. And that part of the article is really where I started thinking okay, this is where this kind of connects into interest on my research side. But some of the interesting things they found were that, that his size of his brain was actually smaller than the average male brain, that there were certain regions within the brain that had a higher number of glial cells to neuronal cells, and glial cells have, for a large part of the neuroscience history have been not necessarily ignored, but not valued to quite the same extent that neuronal cells have been. Probably until the past 20 years have they really not been in the forefront as much as neurons have. But a lot of people now have shown that these cells are actually very critical to the brain, to normal function, to the health of neurons. And so finding regions of his brain that had a higher number of glial cells to neuronal cells was interesting to a lot of people, although that difference was only significant in one area. And then they found that there were other things that were quite interesting, like there were no significant signs of aging in his brain. They used a stain that typically accumulates with age just in the average population. And at an age of 76, the stain was almost non-existent in his brain, which I thought was interesting. And then there was also a couple of regions where there's typically what are called fissures that connect different parts of the brain together. And at least in one area, they found that was missing. And so there was a lot of discussion about how the connective parts of the brain were different, maybe not significantly, but at least trended towards being different from kind of the average male brain around that age range, and how maybe that was allowing him to have increased connectivity between neurons that allowed for this, more extensive and more in-depth processing. And some of these regions were tied into language and math. And so I thought that was interesting, in addition to, the whole component of the fact that this pathologist basically took the brain, cut up into slides, kept a lot of these slides in a beer cooler, in a hiding place in his own home. And as of now, I think there were 5 boxes of slides. There's only one set that's complete, and that's at the Natural Museum of Health and Medicine. And then there's another set of 46 slides that are at the Mutter Museum. The rest are all missing, and the eyes nobody knows anything about other than that they're believed to be in a lockbox somewhere in New York. So I just thought this was all very curious. But, one of the things we're interested in is how microstructural differences within the brain could give us information about brain function, particularly in the presence of injury. And so that was, that tie to it with the mystery component, and kind of this absurd, a pathologist just decides randomly to literally basically steal Einstein's brain without permission from anybody to explore it, was fascinating to me.
We'll get back to the microstructural differences thing shortly. But the thing beyond the fact that people are running around with slices of Einstein's brain, I kind of have this kind of picture in my head of these people running from city to city selling this, and it's kind of black market Einstein's brain, is, a lot of points in the article. And I think the article rightly talks about the amount of uncertainty in any of the conclusions. Like, you can't draw conclusions from one person relative to the population.
Absolutely.
And that pertains to actually a lot of your research, it seems like. So we'll get there. And maybe this is a good way for me to segue a little bit. You also sent me a nice review article you had recently written. And let me read basically the first couple lines of it. And this, actually, this might be from your website, but your review article has something similar in it.
Yeah.
So you say, despite significant financial investment we have made, we are still struggling to fully understand and adequately treat the majority of complex diseases. If we look at the brain, neurological diseases account for 13% of the global burden of disease, and as a result, $700 billion a year is spent trying to treat them. Drugs that are used to treat the injured or diseased brain also take about 35% longer to be developed for use in humans compared to drugs for any other type of disease. That's a pretty substantial statement, so why don't you unpack that for us?
There has been a ton of technology development, basic science investments, clinical science investments in trying to treat a lot of very complex diseases. And I'm thinking like everything from cardiovascular disease and diabetes to a lot of the things that interest us, which are in the neurological areas, to things like autism spectrum, Alzheimer's, depression, anxiety, anything within this realm I'm broadly classifying as a complex disease. We spend a lot of time and a lot of efforts in trying to design technologies that can either help us better understand these diseases or try and treat them. And there's been a lot of success in preclinical literature to show that they actually, that technologies can help us better diagnose and understand these diseases and also potentially treat them. And this comes back to the proverbial, media statements that, cancer was cured in 20 rats in the lab. And, that gets this big to do about it. And so one of the things that sort of motivated us in writing this review and kind of motivates our research is that there seems to be this really big disconnect between effort put in and outcome and output. And the statistics I even give on my website or in this review article are also out of date, even though they were just like a year ago. I think we're over close to 900 billion now in a year in treating neurological disease. And that's largely because we have an increasing number of aging people that are living longer, so they're more likely to get diagnosed with some of the diseases that tend to onset later in life. There's this big, in my mind, missing rationale or reason behind why things can be so successful in preclinical settings and then don't translate into clinical settings. And so one of the reasons that we're really interested in thinking about it that way, and I think this is where the chemical engineering view is really powerful, because this is a scale problem in my mind. It's scaling in a lot of different ways. It's scaling in just volume and length scales, going from preclinical models to humans is a difference in volume and length scales. It's scaling in
real quick.
Oh, yeah.
Sorry to interrupt. So clinical means in people, right?
Right.
Just to be clear.
I'm thinking clinical in people. Yes.
Okay. Preclinical would be rats or something like that.
Right. Preclinical would be, I think, anything that is considered to model an aspect of a clinical condition. So I would even include preclinical as being in vitro models, microfluidic assays. There's a lot of work done in that realm, like in cell culture and in microfluidic systems, that allow us to probe very specific aspects of a disease that then can help or aid in technology development for actually treating the disease. So I would even include that type of work in there as well. And that's a much broader definition, I think, than what many people tend to think of with preclinical. Usually it's in vivo animal models. So anything from a mouse up to, a non-human primate. And that alone, when you look across scale of preclinical in vivo models, is also different in terms of scale that we're talking about, which is part of why I'm fascinated by diffusion itself. But that's I guess probably a down the road discussion. But one of the things that I think is really unique about bringing the chemical engineering approach to the scaling problem is the fact that chemies are very well trained to think about molecular to whole system scale. And so what happens at a molecular level and how does that drive then our ability to scale up a process or a product or a concept into something that can be relevant to a large population of people. And ideally, it's impact a large population of people in a positive way. And that was kind of how chemie has always been presented to me in my mind. And so one of the things that we are really motivated by is how can we take the huge body of preclinical literature that's out there for neurological disease and think about the challenges associated with scaling up, integrating that information and scaling up that integrated information to humans, and where are the missing pieces of information, and can that potentially, those missing pieces of information, can filling that in potentially help us better understand these diseases so we can design better delivery, systems to get a drug to the disease? Could that enable us to get drugs more quickly into humans to treat these diseases, which might address the fact that the drugs for the brain typically take much longer to actually get into clinical application than they do for other diseases. So we're kind of thinking about it from how do we go from a small scale to a large scale and find useful ways to fill in that missing information that is actually going to have some impact in either how we design or direct therapeutic intervention for these neurological diseases.
Well, first of all, it seems like this would be relevant to other diseases outside the brain. But the other thing I'm hearing you say is that one of the factors that may be underappreciated is just the difference in size between humans and preclinical models.
Right. And this is something, yes, there is a difference in size. And I have actually this quote that I read many years ago, actually at the start of my PhD, which was one of the reasons I got interested in diffusion. And it was a quote from a paper, actually a very lowly, not high cited paper from several years ago that actually almost 2 decades ago, that says the key difference between a mouse and a man for some drugs is sometimes simply that the man is bigger, but the drug still diffuses the same distance in a given time. And
Right.
That quote, for whatever reason, just stuck in my head because I was thinking, physiology is largely driven, one of the underlying processes in physiology is diffusion. The ability to get oxygen between blood vessels and cells is a diffusion driven process. And the same with a lot of other nutrients and in the brain with neurotransmitters and other signaling molecules. And so this sort of concept of the fact that when we scale from something as small as a mouse up to a human, when we actually go through that process, we still have to rely on the underlying fundamental process of diffusion to do whatever it is that we need to do. And so then the sort of interest for us was, how can we actually better understand what diffusion means and looks like for therapeutics, not just for water, which is what most of the clinical studies look at, is diffusion of water. And so we wanted to understand, okay, what does diffusion look like from a therapeutic perspective? And then how is that something that we might be able to, if we understand it, to be able to better control it or maybe direct it in some way, better, direct that transport so that we can actually get therapeutics to be more effective in their delivery mechanisms, with the fact that, we're still going to be working in the context of what diffusion actually is, since that's the baseline fundamental physiological process. So that was kind of that motivation, that in 2006, I read this quote, I think it was 2006 or 2007, I read this quote and was like, oh, this quote is it's such a simple concept, but it's a very powerful one.
It's a really fascinating point, because in chemical engineering, when you have to move something quickly over a long distance, you're not doing it via diffusion. You do it via convection.
Right.
And you don't have that luxury in many parts of the body. In some parts you do, but other parts you don't. And so you're stuck, right? Wow, that's a fascinating thing to think about.
Yeah, and so it's actually, the convection component is actually really interesting. And some of the work that I did in Justin Haynes' lab at Hopkins, and that one of the students that came after me did even more thorough and very beautiful work following up on what I had started, shows that if you can't diffuse, it's much difficult to convect you. So if you are a molecule of some kind and you actually don't have the capability to diffuse, it also reduces your ability to be convected. And there's also work done by Mart Saltzman at Yale that has shown that having the ability to basically leverage diffusion gives you a much greater ability to be able to be convected. And so that was actually something largely overlooked, at least in the clinical literature, when a lot of clinical trial studies, mostly in the cancer field, looking at brain tumor treatments, showed that even with convection enhanced delivery, when you're basically just trying to bulk push something into the brain, you actually don't get as large of a distribution as one would expect, because the things that you're still trying to push in the brain aren't actually capable of diffusing. They're not capable of avoiding interactions with cells that might, take them up, and they might not be the cells you want to take them up. They might not be capable of avoiding interactions with proteins within that tumor microenvironment or within the brain microenvironment. And so that inability to kind of avoid unwanted interactions still applies and affects things at the diffusive level, but then in scaling up to convecting it is still a relevant enough factor.
Mark Salzman was the person who convinced me to be a chemical engineer.
Oh, really? He does really beautiful work. I have enjoyed following his work over my entire time, basically since joining Justin's lab at Hopkins, where Mark was before, actually. And, some of the analyses that he does and really kind of understand what are the fundamental processes that drive our ability to deliver therapeutics. And for me, particularly in the brain, I find really nice and really interesting and very thorough too, which is hard to do in some of these, analyses.
Yeah, I crossed paths with him at Cornell when he was there, after Hopkins, before Yale.
Right.
But that's how I became a chemical engineer, even though I work in semiconductors.
Yeah.
So let's talk then a bit about nanoparticles.
Right.
The podcast is called Nanovation, so let's try and make a connection here, although I tend to very loosely connect things to nanotechnology sometimes. Yeah. So you do a lot of work using nanoparticles as therapeutics or to deliver therapeutics. Can you talk a bit about what that means? And also, because we've talked a lot about nanostructures for other applications like solar or electronics, kind of talk about what are the key differences between these two related but unrelated topics.
Yeah, so we use nanotechnology mostly as a tool. And by a tool, I mean we actually like to use it more as a way to probe a tissue environment. And then because we're using it as a tool to probe a tissue environment, we feel like that information is more readily translatable to then using that same type of nanoparticle platform as a therapeutic intervention. So we're staying within the same context. How we probe and then how we intervene are all kind of coming from using the same type of system. And so the nice thing about the nanotechnology capabilities is that, as you know, nano is very tailorable at the atomic and molecular scale. And that's the scale at which most biology operates. And so having this ability to really tailor something at the same level at which biology operates is, I think, very powerful. It also allows you to have a lot of control over what exactly you're making. And that's where I think, the ties are between other fields that use nano. A lot of times the properties that you have at the nano scale are unique and can be utilized in a way that maybe you wouldn't have when you're looking on bulk scale or when you're looking, even just at like the micro scale. But then being able to fine tune those properties, I think, is actually a very, very powerful component in whatever field that nano is applied in. And I see this with some of my colleagues who work in solar energy related applications, or who work in renewable sustainable energy related applications, or in the battery field. We're really being able to control and tailor each individual component of building up a synthetic inorganic nanoparticle, for instance, can actually allow you to really, really tune the properties to what you need for the application. And that's, I think, from a therapeutic perspective, very empowering, because if you want to get a specific drug to a site in the body, what a lot of nanotechnology has been used for is not only to protect that drug from the body's very efficient clearance mechanisms, but also increase a drug's solubility, to increase the amount of drug that you can get into a physical space, because a nanoparticle has a much greater surface area to volume ratio than, like, say, a protein does, for instance. But then also to be able to tailor the components of the nanoparticle to take advantage of physiological aspects like blood flow and getting, marginating from the center of a blood vessel to the wall of the blood vessel to then cross into a tissue space, putting on a targeting ligand that's specific to a receptor on a diseased cell that allows you to potentially get increased uptake in just those diseased cells, having components on that nanoparticle that can be reactive to the environment. So if you have a change in pH or a change in hypoxic oxygen content within the tissue, or if you get intracellular and you want to only release within a certain part of the cell, having chemistry that's built into the nanoparticle that allows you to take advantage of those sort of natural physiological aspects, I think is a very powerful component of it. So it still comes down to how much can you tailor it, and can you tailor it at the level that biology operates at? And I think that's a very, empowering concept that, if leveraged in the right way, I think can actually be very impactful.
So when I think about nanoparticles for a lot of the work I do, in this case, they're crystalline, but it's that crystal structure particle itself, not necessarily anything that that's attached to it,
right,
that give you properties of interest. And the sense I get from my understanding of what you do is that oftentimes the particle itself is less important than what you attach to it that does a lot of the work.
Yeah, so I think actually I would kind of argue the flip of that the particle itself, even if it might be simpler or bioinert in the same way, so it doesn't, cause any actual effect within the body, is your way of improving a drug's ability to do its job. And so I think that one of the interesting things, particularly in the brain field, is that there are, if you look at the CDC's recent analysis of this, they've shown that I think about 7,600 different therapeutics have been attempted in treating brain diseases, but about 97 or 98% of those can't actually even access the brain or get into the brain. And so one of the interesting things is that a lot of drugs can actually be very effective if they can get where they need to go. But the problem of getting where they need to go is significant. One of my postdoc advisors, I think, sums this up very nicely. He gives this fantastic example where he says, if you're a drug and you're a drug in a nanoparticle and you're dropped, let's think about dropping a soccer ball in the Indian Ocean, and you want that soccer ball to get to, we'll say, to Puget Sound in Seattle. There's nothing about that soccer ball that's going to make it get to Puget Sound in Seattle, right? Because it's going to just by luck, if it follows ocean currents and it follows flow, and I'm not obviously an oceanographer here, so somebody's probably going to say, well, there's no actually, currents that are going to, but, point is that the soccer ball relative to this physical space it has to move in is significantly different. And so you have this just volume difference and potential surface area difference. If you think of every place that soccer ball could land on even just the American coast, it's huge. So what would make it go just to Seattle, or what would get it to just Seattle? And so drugs have the same problem. They're just going to touch everything they come into contact with. There's nothing that directs them to go to just the cell that's sick. It's going to go to every cell. And this is why you see things like chemotherapeutics cause skin issues and hair loss and GI tract issues, because you have a lot of cell turnover in those areas, and these drugs are touching every single cell they come into contact with. And so I think drugs can actually be very effective on their own, but the nanoparticles' power is to be able to take advantage of some of those physiological aspects that could allow it to be targeted more specifically, so that the drug isn't going everywhere. It's going more specifically to its site of interest. If you can get it to its site of interest, it's much more effective. The drug has the opportunity to actually be much more effective in what it does.
Okay, I want to make sure I understand this. So the kind of foundational approach would be something like, I have a particle and I put the drug inside of it, and then I decorate the particle with various things that help direct where this particle goes so that I can bring its carrier to the site where it's needed.
Right. And sometimes decorating it with, various things is not necessarily decorating it with things that are active, like that would, back to that example of, decorating it with something that is going to specifically recognize a receptor on the cell. Sometimes it's decorating it in such a way that it either keeps that nanoparticle from being recognized by the body so that it doesn't get cleared out by the macrophage system, which is very efficient at getting things out. Sometimes it's to keep it at a certain size so that the body's natural filtration system doesn't filter it out. So for instance, the kidneys are really great at filtering out things that are smaller than 6 nanometers. So sometimes having a particle that's slightly larger than 6 nanometers can keep it from getting cleared out of the kidney. There's a lot of really beautiful work that's shown how the shape of that particle, as well as its size and its surface coating, can dictate how it moves from the center of blood flow out to the wall of the blood vessel and then gets across the endothelial cells at that blood vessel wall. Controlling just the total physicochemical property space of the nanoparticle, even without putting active agents on it, can actually be very useful in kind of dictating where you want it to go in the body. Certainly some nanoparticles on their own have effects. There's a lot of really nice examples with dendrimer-based nanoparticles, which are really, generally fairly small, sub 20 nanometer particles that are, like the name sounds, like these tree-like branched, flexible particles that actually much more act like macromolecules. And they are, in some examples of dendrimers, they are actually innately, without any drug attached or associated with them, antibacterial and antimicrobial. And so there's actually, at least one clinical use that I'm aware of offhand, or at least remembering offhand, where these dendrimer nanoparticles are loaded into a gel on their own, no drug attached, and they're used for, bacterial infections in the vaginal tract, for example. And so some particles can have an innate ability without a drug, but the majority of them are designed to try and increase the delivery of a therapeutic or a diagnostic, I should say. Those are also important as well.
So in terms of making this work, and I'm just thinking about, I guess this is a kind of a technical question, maybe too technical for the podcast, but let's try it anyway. How do you attach multiple things to your particle? I mean, I think about what we do, and it's hard enough to get the right surface chemistry that's homogeneous across the surface, but it would seem that you need various different chemistries that all contribute in their own way, or maybe synergistically, to do different things to help that particle get where it needs to go.
Generally, my answer to that is you have a really good chemist on hand, because those guys are like so skilled at really doing just beautiful, controlled, predictable chemistry. I have to say, I worked with a lot of fantastic chemists while I was at Hopkins who had much greater understanding and skill to be able to control from one molecule to the next exactly what was displayed on the surface of a particle, for instance. My sort of more general answer is that I think it's very dependent on the nanoparticle platform, on how much control you have on what is displayed on the surface of a particle or what the composition of that particle is. Usually you know what your starting materials are, but one of the things I think at least we run into is once you put those starting materials into a formulation so that they complex into a nanoparticle system, knowing what you end up with where in that nanoparticle is actually quite difficult. And that is including a drug. So for instance, polymeric nanoparticles are, really beautiful systems for controlled release aspects of a drug. Based on the makeup of the polymers that you put into the nanoparticles, you can control how much and how quickly a drug releases over time. And that's a really nice component. But where that drug actually is physically distributed within that nanoparticle is much harder to identify. And the things like emulsifiers and surfactants that you need to stabilize those nanoparticles when you're making them are much harder to identify where they are within the particle, if they're on the surface, how much of them is still present after you collect these nanoparticles and wash them and try and purify them. There's a lot of formulation aspects that are still being explored for certain nanoparticle systems. Other nanoparticle systems, and I'll include some of the inorganic semiconductor particles that are used a lot of times for imaging applications. Like one of our collaborators, Vince Holmberg at the University of Washington, makes really beautiful quantum dot-based nanocrystals. And they have really nice ways of synthesizing the core of the quantum dot, adding on the shell, and then adding on ligands onto the surface. And they can control that through, really, really nice stoichiometrically defined chemistries. And so I think because it's more of a synthesis buildup process, there's a lot more of an idea of what your final product looks like. But as you said, there's still this challenge of knowing how uniform those ligands on the quantum dots are on the surface. And as far as I know, I don't think there's a way to estimate that you have this exact number of this one ligand on the surface. I think that's still, you can get a range, and a pretty good range. Not exactly like you definitively have 18 amine groups on the surface of this quantum dot. And I would say the same is true for the dendrimer nanoparticles. You can grow those to know the number of total functional groups you have on the sort of end branches of these nanoparticles, which would in theory be your surface. But whenever you conjugate on a drug, for instance, I think the closest I've seen anybody be able to narrow it down is to say, okay, we maybe have 18 to 20 drug molecules, but we couldn't say we definitively have 19 drug molecules. So I think there's still some limitations in knowing exactly how much is on the surface and what that surface actually looks like with a lot of these systems.
So can you talk about how you would run an experiment? So you've made some particles, you think these are the best particles ever made, and you want to study them and see if they are the best particles ever made. What does an experiment look like?
It covers a pretty broad range of scales, I would say. So whenever we're formulating, if we take some of our biodegradable nanoparticles that would be loaded with a drug, for instance, we often formulate those particles typically through fairly standardized processes that are used in the field. So things like double emulsion processes or nanoprecipitation processes, which for most people is going to look relatively simple. You basically mix an organic phase with an aqueous phase, add some energy to it, have a surfactant in there to stabilize it, and you're popping out some nanoparticles.
So real quick, I think the good analogy there is like oil in water or like salad dressing, where you shake it up, you get a bunch of bubbles. Imagine you take those bubbles and then you polymerize them so they all become little particles. Yeah, right? Exactly. That's more or less what you're talking about.
Yeah, milk is a good emulsion example as well. Right. There's a lot of great ones out there. And so you're just thinking about, adding in enough energy so that you can get these to a controllable size scale. And typically we're targeting something around the 60 to 80 nanometer range. And we want, a drug stuck into them as well. So what we often do after that is we try and do a fairly extensive characterization based on the experimental techniques that we can do. So we'll run things like high performance liquid chromatography. We'll run dynamic light scattering to get size and estimated surface charge and polydispersity. We'll do some electron microscopy to look at morphology and distribution, another way of visually looking at distribution of the particles. And then we certainly look at release of the drug from the particles. And that's usually all done in what we would say is an in vitro system. So really just testing these particles in a solution, potentially a saline solution. A lot of times we evaluate these in cerebral spinal fluid, which is our closest estimation to what interstitial fluid in the brain is like. A different story is that we found that there's actually quite a lot of differences between how nanoparticles behave as colloidal suspensions in cerebral spinal fluid versus how they behave in saline or blood or anything like that. But that's a different aside.
I have an aside.
Yeah.
Where do you get cerebral spinal fluid from? Is this the 7-Eleven down the street? Where's it come from?
So we can artificially make it. And so typically we use artificial cerebral spinal fluid, which is really just in comparison to saline, actually just has a lot more ions in it. So ions like calcium and magnesium and sulfates, as well as just a higher total concentration of ions. The challenge with making artificial cerebral spinal fluid is that it is not a buffered solution. And so in the body, it is constantly buffered, but it itself is not buffered. And so one of the challenges that we've had and anybody that's worked with this has had to do is how to maintain an actual consistent pH throughout an experimental window and an appropriate level of CO2 and O2 to keep that pH constant, because in the body it's constantly being buffered through exchange with blood. And so that's one particular challenge with working with cerebral spinal fluid that doesn't happen when you work with, saline, for instance, because usually saline in the lab setting is phosphate buffered. So we make it, but then we also have to be really, really tedious about keeping it buffered so that it's at an appropriate, at physiological pH, so around 7.2 to 7.4.
Okay. Sorry. I was just really curious.
Yeah, no, it's actually, that was enough of a hiccup that we had there's a lot of, small discussions on the side that talk about, the challenges of working with cerebral spinal fluid because it's not buffered. When it's outside of the body. So no, it was actually, we have some interesting work that we'll be publishing soon on how colloidal stability is very different in cerebral spinal fluid, but also the challenges in actually testing that outside of the body, and how that could be potentially an important factor to be exploring more, because so many things are then stuck into the brain or attempted to go into the brain, and the environment they obviously come into contact with there is different enough from the environment they experience in the blood, or even I would say in other organs, which have different ion compositions than the brain does. So yeah, we're hoping to get that work published soon, which we hope will be of interest to somebody other than us. But yeah, once we do the in vitro characterization, which, as I mentioned, we mostly do in cerebral spinal fluid, we actually have a characterization step where we look at how these nanoparticles behave in living brain tissue slices. So these are brains that we fresh harvest from an animal, and we culture these slices to keep them alive, but also to make sure that their 3D architecture stays intact, so that we have usually about 300 microns worth of tissue that we're working in within the Z direction at least, and then the slice is usually a slice that basically is the cross section of the entire brain. And so we will put these particles, any particles that we make, into these cultured brain tissue slices, and we will track those nanoparticle behaviors. And we're usually tracking how these nanoparticles behave on the order of a couple of seconds. So trying to get as close to real diffusion as possible. And we've had a lot of great collaborators who have, with some companies who have really worked with us to try and get the best possible imaging set up for live tissue imaging to capture as close to real diffusion as possible. So we're talking right now, we're at about 100 frames per second is the rate at which we capture these videos to look at how individual particles behave. And so what we are specifically looking for is, can they move? Basically, can they diffuse around? And then if they don't have a surface coating on them that would keep them from getting into cells, can they actually get into the cells that we're interested in having them get into? And so that's a characterization step that we are specifically interested in before we actually move into any sort of in vivo studies, where we would do what I think is kind of more typical of the drug delivery field, which is to inject the particles either directly into the organ of interest or inject them into the bloodstream and see how long it takes them to get to the target of interest, how much gets there, and then where they go once they get there. And so we certainly do those studies as well. And then in an injury model, we look at effect, and that effect can cover a range of from pathology analysis. So doing, kind of like what somebody would do or did with Einstein's brain, although we, in theory have permission to take the brain and look at it. Maybe not from the rats or any other animals we work with, but at least from the people that approve us working with the rats. But we look at sort of the pathological side to see impact, as well as behavioral, and also just at whole brain changes. So for instance, when you have a stroke, a good portion of brain volume can be lost. A lot of tissue can be lost. And so looking just at the sort of gross brain, the total brain as a whole, can tell us something about whether we had a therapeutic impact or not. And so the way we evaluate the sort of efficacious response covers as much of a range as we possibly can, so that we can not only see whether we truly have any sort of therapeutic effect, but also understand perhaps what the mechanism of that therapeutic effect is. And so we try and span that entire range from in vitro to in vivo. But I would say where we feel like we have kind of a unique angle is that middle step of looking in what I would call ex vivo, so in those live brain slices, and really trying to characterize that diffusive behavior, and then what that means in terms of cell uptake or compartmentalization within the tissue itself.
Fantastic. I think that last point there about the range of things your group works on is a good segue into the last thing I want to talk with you about. And I'll use your TEDx talk as a jumping off point. So you gave a very nice TEDx talk. UW had one of these a couple years ago, and it was titled Specializing in Not Specializing.
Yeah. I could probably come up with a better title.
Well, it's a fine title. It's a fine title. And the first thing I would say as a way to start the discussion is that lots of academics would completely disagree with that statement.
Right. I faced that actually quite a bit when I was interviewing jobs. So I don't disagree with their disagreement. But sorry, you probably had a question associated with that.
Well, I wanted to use, not really, actually. I wanted to hear you talk a little bit about what your point was in the TEDx talk. I'll put a link in the show notes. And actually, based on what you just said, did you give this talk before you were searching for a faculty position?
No, actually, it was right after. So it was right after I had joined at
Okay.
UW, or not too long after I had joined
Okay.
at the University of Washington. But yeah, so I guess it kind of came out of mostly frustration with this sort of preclinical to clinical translation area, as well as with the drug delivery field. And I'm not saying frustration to offend anybody. I just felt like there was a lot of reluctance to make connections because of the complexity of the problems that we were trying to tackle. And so what I mean by that is that when I was doing my PhD, I felt like I got a really good understanding of polymer nanoparticle formulation and design and application in vivo, at least from the perspective of how you evaluate things like the kinetic profile of the particles, their retention, their clearance, and their therapeutic impact. But what I felt like I didn't know at all was the underlying physiological mechanisms that were taking place and what that would mean in terms of how we would be implementing those therapeutics in the body, and then also how we would be analyzing their outcomes and how that then connected to the heterogeneity of typically these diseases that you see in the patient population. And yeah, I didn't feel like the way that we were approaching it actually gave us an opportunity to account for that heterogeneity, at least not from sort of a underlying fundamental understanding of what is actually driving, the differences from person to person within the same disease spectrum in the first place. And so I went into a postdoc area actually that most people would say was completely out of left field for a chemical engineer to go into. So I chose to work with a very small lab in critical care medicine, where their research was mostly in the neuroscience space, who I thought were just doing really, really fascinating, cool things. So they were working a lot on developing models of neonatal or pediatric brain injury. So any sort of injury that can occur before, during, or after birth, and then also injury that could progress into early childhood. And not only did I know that that was a fairly underserved area from the perspective of technology development, but it was also a very complex area to me, because not only do you have the disease or injury process ongoing, but you also have potentially normal development competing with that. And I thought that that sort of complexity was actually a really interesting space to be in. And so I sort of threw myself into this postdoc, not knowing really anything about neuroscience and certainly not knowing anything about pediatric brain diseases, and found that what I had to basically teach myself to do was to collaborate with as many people as possible, but also go in knowing that I didn't know anything. And so like basically going in with blinders off. So like not making any assumptions, kind of coming to the table, not with an expectation of giving something to whoever is coming to the table with, but more with an expectation of, all right, let me see how they're thinking about the problem from their perspective. Let me try and understand the language they're even using, because jargon is a huge challenge within integrating a lot of fields, but also just to see what their sort of goals and what tools they're using and how those tools and goals might align with the tools and goals that I would potentially be using. And in going through that process, I actually found that there was very little infrastructure in place to really enable students to do that in a constructive way. I fortunately had fantastic mentors who helped me navigate that process and helped me kind of cut away the fat on things. There were certainly, from the neuroscience point of view, a lot of questions that maybe were a little too detailed and I didn't really know. But then there was also things on the, chemistry or drug delivery side that I didn't feel like were necessary for me to know, because I thought the physiology or, the biology were going to dominate over what the sort of chemistry or the nanoparticle technology would be able to do. And so I had mentors to help me navigate that space, but I had 3 during my time. And those 3 all covered, came from very different backgrounds, had different degrees even in terms of like MD versus PhD, and certainly were in different fields. And so I think that process really enlightened me to the fact that there are feasible ways to gain expertise and insights beyond just what you have trained in your PhD. But those are necessary things to be able to do in highly interdisciplinary spaces, particularly because, and this is purely my belief, my opinion, my philosophy, I think there's a lot of lip service given to being interdisciplinary. But what I've seen most of the time is that interdisciplinary means that you take one person, they have an expertise, they do something, and then they hand it off to somebody else. And handing it off to somebody else, in my mind, is not actually integrating the information. It's kind of taking two things and sort of just sticking them together however it seems they best fit. But it's actually not finding the optimal way to always integrate those two things together. And it's challenging, right? Like you'd have to learn enough of the other side to be able to see where that most, optimal integration might be. And that does require, usually you learning jargon, learning, another viewpoint, learning another approach. And there's just, a lot of times not that much time for that. And maybe not also always the motivation to do that. And so I found that, what I really wanted to do is find ways to truly have more I guess it's not even interdisciplinary. It's just integrated training. So how do I teach students, to become experts in areas where they can have impact, but also to become experts in ways to parse information from other fields, internalize that information, integrate that information into their work so that they can better interface with those fields to have impact. And I think that's something I'm trying to do in my lab program. I obviously only have, 30-year grad students at this point. And I think they're doing really well, but that's my view. So we'll see how that plays out. But I do, they spend a lot of time thinking and learning neurobiology, just like they spend a lot of time thinking and learning chemical engineering principles and how those apply to nanotechnology. And I think my role as their PI is to help them be able to tailor information to appropriate audiences when they need to. So in full transparency, they need on their general exam to be able to show that they are capable of doing chemical engineering fundamentals and applying those in a research setting, and then going forward with being able to define, design, and analyze experiments that are going to be, potentially successful or ask the right questions. But then when they go and they meet with a clinical collaborator, they need to be able to have the ability to kind of morph into a setting where they can see things from the clinical collaborator's perspective, understand the terminology and the challenges that are associated with whatever disease it is that they're trying to address, and then also be able to do even simple things like experimental design that's going to enable us to get the most useful information out of both our engineering side of things, as well as, potentially the neurology or neuroscience, clinical or basic science side of things. And I think it's actually a trainable thing to be able to do, but it takes an intentional approach to say that you don't have to just be an expert in what your degree says you're an expert in. There is actually benefit to at least learning the language and the tools that are out there. You might not be the expert user in those tools, but you can at least have an intelligent conversation about them.
Yeah, it sounds like what we need are oxymoron students, right? Students that are really deep in their discipline, but that are broad at the same time. And that by having some amount of breadth, they can make those connections in meaningful ways.
Right.
I agree with that a lot. Like I have had some students who are phenomenally good analytically. They get the fundamentals. They could potentially model a bunch of stuff. They think about problems deeply. They search the literature. And then they never go into the lab and do the experiments.
Right.
Or at least they do one experiment a week instead of 4 experiments a day or whatever, right? Yeah. And then I have the students that are running experiments all the time and not thinking deeply about their results and, the underlying mechanisms. And so it's really, I always say that you need to have a balance of that. You need to get in the lab and do the work, and you have to have the foundational mechanisms. And it's very similar here in terms of being broad as well as deep in your discipline.
I would also add to that one of the things I found perhaps most troubling in my training and then in actually searching for a faculty position was the power of making connections was not as valuable as whatever the two things being connected were. And I think that, since we're in an increasing multidisciplinary, transdisciplinary, interdisciplinary, whatever version you want to put in front of disciplinary world, that ability to actually make connections to me is maybe the critical point that we're not training for it. This connection between preclinical and clinical is a connection. So how do we get from preclinical to clinical research in a more successful way? I think that, there are certainly a lot of people doing research in that space, but is it enough? And are we emphasizing that sort of translation aspect, that purely from a connection perspective, how do we actually take the information that we are getting in those preclinical studies and, connect it in a useful way to the clinical challenges we're trying to address? Are we doing that truly? Are we truly training for that? I'm not certain that we are. And so when I was going through, and I mentioned this in my TED Talk, when I was going through my interview process, I sit at kind of the middle of a lot of fields and I like that. But I've found a lot of benefit in that as well. And we pull in molecular biology techniques, we pull in neuroscience techniques when we need to, we pull in engineering techniques when we need to, we're now pulling in data science tools, because those are valuable. So, it gives us the opportunity to pull in tools when we need to, but I was accused of being a glorified matchmaker and not having any depth. And that was really frustrating because I felt like, I was taking a different perspective. And that perspective was, maybe actually making connections is the missing component for many things that we're trying to do right now. And so I think that one of my goals is how do we, is to find ways to implement training in for students that want to. I agree with you that we need a balance, but there are students that want to be at that interface for the purpose of being able to make valuable connections that could enable fields to move even farther or could enable technologies to actually translate from, preclinical to clinical studies. And how do we create a training space for students to be able to do that so that they are not then, interviewing and being accused of just being glorified matchmakers. They're actually seen as having value in themselves, like having value in the fact that they're making those connections.
The people that say that are the same people that think Apple doesn't do anything useful.
Right.
Right. Yeah. Because, I mean, they don't make a lot of their chips and they just have a certain function that they integrate and do a phenomenal job integrating. Right. So it's really hard to argue that what they do is not useful. And I find it hard to argue that integration and interdisciplinarity and the way you're describing it is not useful either.
Yeah, it has to have value on its own. I think it's not necessarily a means to an end. And there are, I think, people that appreciate that, but then training for that can be overwhelming because then you have to be, confident with taking risk. You have to be comfortable with basically being wrong a lot of the times. And you have to be willing to kind of put yourself continuously in uncomfortable positions to talk with, people who literally could sit there and say things for 15 minutes and you could have no idea what they're saying, even though they're using some of the same terminology that you're using. That happened to me in my first year as a grad student when I met with a neurosurgeon. And so, there's this like it's a very overwhelming space, but I think there has to be value on its own in that connection component and not just it be value to get, as like a means to an end. And I think that there is a way and a good way to do that, but that doesn't mean that there's less value to the people on either end, those that are going to apply that, whatever connection you make, and those that actually are doing the really deep fundamental analyses, digging into the underlying basic principles. Both ends, I think, are critically needed, and I think we train well for those ends. It's just that middle piece that I think a lot of times is missing.
Towards the end of your towards the end of your TED Talk, you had a series of questions. The first one was, what if the challenge is not in designing new materials, but in finding better ways to connect and implement the materials we already have?
Yeah.
And I think you asked that question and the two other questions, which people can watch the TED Talk if they're interested, from the perspective of specializing in not specializing, right? That by not specializing, you'll find new ways to do things with what you already have. Is that right?
Yeah. So I think it kind of comes down to the training paradigm that we want our students to be resourceful, and we want people in this day and age to be resourceful because resources are out there, and in some ways they're much more accessible to us than they used to be. And so I think that what I like to throw out there is that there's actually a lot of very beautiful tools and technologies, but perhaps they're just siloed in areas that we might not be able to see because we have the blinders on for our field and the way that our field approaches something. And I think there's a lot of benefit in kind of taking a step back sometimes and saying, okay, the tools exist. Maybe I'm just not either looking for them in the right place, or maybe I'm looking for them to be used only in the way that they're currently defined. And so there could be ways to kind of integrate those tools or use those tools in a new way, or to connect tools that haven't previously been utilized before. And I think that it sometimes just requires taking a step back from kind of our day to day. This is what I know. This is what I'm good at. This is what I've trained in. I think, it's great to have those skills, but I think there's a lot of there's a lot of benefit to being able to kind of step away from those skills and say, okay, there are more skills or more ways that I could do this. And it doesn't have to just be with what I've become so specialized in. And to me, it's more of a philosophy and an approach to doing science that I hope to train into my students, but I also would like to see, because I think it could just enable us to get farther and have more impact. And there's a lot of historical examples of where connecting existing materials in a different or a new way are I think, very, very empowering.
So I think it's important to point out that you don't have to be doing interdisciplinary work for this to be really important.
Right.
And there's plenty of times, even in a well-defined discipline, where people had everything at their fingertips, and it took someone to come along and say, if you rearrange it this way, look what happens, right?
Yeah.
And I actually think chemies were not necessarily well trained, but we're kind of familiar. We're primed. That's right. Yeah. That's the right language. Yeah.
We're primed to do this based on how we educate our students, because we educate our students oftentimes without an application in mind. We fundamentally train students to know thermodynamics, kinetics, transport, without necessarily having a specific application in mind. And then one of the reasons I love chemical engineering so much is it's such a broad field. And it's a broad field because when you train to understand the fundamentals without the application, you can then take those fundamentals and tailor them to whatever application you need. And I think one of the reasons I chose to teach in chemical engineering is because I wanted to bring the sort of opportunity to students, or at least a viable pathway to students, to say, hey, all of this stuff that you're learning that's been, historically applied to the food and the petroleum and the, manufacturing and whatever else, like traditional engineering industries, is actually very relevant to medicine and to health and to, like global health. And we need more chemical engineers in this space, because you come with that very unhindered, primed mentality that the underlying knowledge that you get is actually a very adaptable and tailorable set of information or skills or tools that can be used in a variety of ways. And so I think that chemies are in a unique space to do it. I think we're just underutilized in applying that approach in a direct way as chemical engineers to health and medicine. And there's certainly a lot of faculty out there that I think that are working towards that. But they might also have faced some of the same challenges I faced, which is like, well, you go too far or you get too much into your application, and then you might no longer be seen as a true chemical engineer. And that's a stereotype, or sort of a mentality I want to try and minimize or get out of the world as much as possible.
I think it's really fantastic to try and do that. And I will say it's not just in your realm, it's in my realm, and I'm confident, because there's two of us who have problems with this, that there's other people who have problems with it as well. Yeah. And the more we can try and recognize that there's alternative ways of doing things, the better we'll all be.
Right.
Let me ask you one more question, and then I'll let you go. So what are your 4 a.m. moments? In the sense, what keeps you up in the middle of the night?
I have 2 levels of answers to that question. One is like kind of the more nerdy answer, which is thinking about diffusion data, and if we're really capturing real diffusion in a tissue environment, and if we can actually use that diffusion data in a way. So it's kind of worrying about our data, because it's such a complex system to work in, and it's really hard to measure real diffusion in a biological space. And so there's certainly that side of things. Right. The other side actually comes back to is more philosophical, and is constantly kind of thinking and trying to be introspective on my role as a scientist and as a faculty and as a professor in, enabling students to pursue what they want to pursue. And I spend a lot of time mentoring students in a variety of capacities. And one of the things that I sort of worry about a lot is that students in this day and age are constantly inundated with information. It's everywhere, and it's 24/7. And I feel like it's getting harder and harder for students, because they're always inundated with information, to figure out who they are without being swayed, by all that information that's out there all the time. And I see a lot of increasing presence of things like imposter syndrome, of self-doubt, of concern that what they're doing or what they really want what they want to do, particularly with their chemie degree, for instance, is not a viable path for them. And I spend time worrying about this because I know that they're capable and I know that they're skilled. And I'm worried about like what the messaging is that we're giving, or that the world is giving them, that who they are isn't valuable, and that, the skills and the dreams and the hopes that they have are not viable. And so I guess there are a lot of 4 a.m. moments where I'm sitting there thinking, okay, how can I address this? And sometimes it's in the context of one student. Other times it's in the context of a whole class, where I see that these concerns are really weighing on their mind, or I see just doubt creep in about something that they feel passionately about, but it's because they've gotten, 25 different opinions in 10 minutes, from a social media response. Right. And then I think this is just a new challenge, in this day and age because of the accessibility of information. I think it actually, having that much accessibility hurts students maybe more than we acknowledge. A lot of people are quick to say, well, the information's out there, and it wasn't out there. It wasn't as easy to find for me, 20 years ago, but it's out there and you should go find it. Yeah, it's out there, but there's a lot more out there too. And so you have to parse it a lot more and filter it a lot more and figure out the quality of the information is a much bigger question as well. And so I find myself worrying about, am I teaching my students to be able to find and gather and identify quality information from many perspectives that allows them to be able to be confident in their decisions, be able to be confident in their dreams, be able to want to stay true to who they are, to pursue whatever it is they're trying to pursue. And I think that's just going to become an increasing challenge over the next, at least 5 years, if not longer. And I always am wanting to figure out ways, and always am open to ways to try and make sure that is an active part of what I'm teaching students to do. Because at the undergraduate level, we only have them for, 2.5 years in chemical engineering at UW. So that's a short time. And then as grad students, you only have them for 5 years. And so, it's never about the short term. It's about what are they going to do in 10 years from now and 15 years from now? And is there something that you can do now to help enable them to be successful in the way they need to be or want to be successful in that time period? And that's a very important part of my day-to-day, even more so than the science. I mean, I love the science that we do, but I'm only one person, and my goal is to train a lot of people to be able to pursue what they're interested in, to have impact in what they're interested in. It kind of goes back to that core of being a chemical engineer, our goal is to build products that impact human life in a positive way. And I think that, since that's my view on chemie, I want to enable as many students to do that, and constantly figuring out ways to do that in an ever changing and inundated world with information, I think can be challenging.
Agreed. So with that, thank you, Elizabeth Nance, for a fantastic discussion.
Thank you. I appreciate it.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.